Okay, so let's take a look at, I guess we'll start with question 8 and then we'll go back to question 7. All right. Get my pen going here. So this says a high school guidance counselor has a pamphlet that says that 20% of all high school students go to a community college after graduation. In a survey of 200 randomly selected high school seniors, 55 replied they plan to go to community college in the fall. Use a 95% confidence interval to test and see if the pamphlet needs updating. Okay, so what I'm going to do to begin with is to copy down the information in that paragraph in our math symbols. So the first sentence, a high school guidance counselor has a pamphlet that says 20% of all high school students go to community college. So that's going to be a percentage of everyone. So that's our parameter P. So we want to see if, or test if, P is equal to 20%. Okay, so then we do a survey. So then we have a sample. And in our sample of 200, so my sample size N is 200, 55 replied yes, they plan on going to community college in the fall. So I'm going to write that as an X value. Okay. All right, so now let's go ahead and start answering some of these questions. Which of these facts would tell us that the pamphlet needs to be updated? Well, what we're doing is we're testing to see if it's 20%. And the pamphlet's going to need to be updated if we have some strong evidence that it's not 20%. And the way that we get that evidence is by looking at a confidence interval. And a confidence interval gives us this interval of values that P could be. So if 20% is in the interval, then the pamphlet does not need updating. But if 20% is not in there, then we have strong evidence that, that the 20% is wrong and the pamphlet needs to be updated. So if we create a confidence interval and it does not contain the 20%, then the pamphlet needs to be updated. Okay, so we're going to come back to that at the end. And remember, this is the thing that we're looking for. All right, now in order to use a confidence interval, we have to check certain conditions. And this is the part that I think can be very confusing, perhaps the most confusing. So I think what I'd like to do, see if I can get, I'm going to open up the notes just so I can show you what this looked like in our notes. Okay, so this is our 3.9 notes. And this is where we started talking about confidence, well, not where we started, but this is where we were summarizing our information for how to go through computing a confidence interval. And the second step was checking the assumptions. We had to check that NP was bigger than 10, and times 1 minus P is bigger than 10. Okay, and we said this is the same as checking that X is bigger than 10 and N minus X is bigger than 10, because X is the number of yeses and N minus X is the number of no's. And this N times P hat works out to be the same as X algebraically, right? If we use the formula, P hat is X over N. Right? And the same thing over here, the N times 1 minus P hat. If I do a substitution and I do some distribution, right, a little bit of algebra, it works out to be the same as N minus X. Okay, so we have these two checks, and then we have this third one, capital N is bigger than 20 times N minus 20 times N. And what these are doing is the first pair of things is checking to make sure our sample is big enough, and then this last one is checking to see that our population is big enough. Okay, so what that's going to look like here is we need N times P hat, which is the same as X, to be at least 10, right? And remember here that we have our X is 55. So N times P hat, which is 55, needs to be at least 10. So that's our first check. And then we needed N times 1 minus P hat, which is the same as saying the number of students who said no. And if I do a quick subtraction, n minus x is 200 minus 55, which is 145. That's going to be the number of people that said no. Okay. So the number of students who said they do not plan to go to community college, which is n times 1 minus p hat, which we just calculated as 145, that needs to be at least 10. Okay. And then our final check was the one for the population. The capital N, which was the population size, needed to be more than 20 times little n. Okay. And 20 times little n is 20 times 200, which is 4,000. Okay. So the total population, which is capital N, needs to be more than 20 times little n, which is 4,000. So that's the three things that we needed to check. So now we go through and we actually, I guess we're, okay, we don't need to actually check them in this one. We kind of did as we selected them, right? Because we said 55 needs to be at least 10, and of course 55 is. 145 needs to be at least 10, and it is. Okay. All right. Now we say, what proportion of high school students surveyed plan to go to community college in the fall? Okay, so if I look back at my sample here, what percentage of people in my sample said yes? Okay, so that's going to be the p hat, which is x over n, right? If I want to find what percentage of people say yes, I take the number of yeses divided by the total number of people. Okay. So as a fraction, that's 55 over 200, or as a decimal, that's 0.275. Okay. I can also see that if I'm going to write this as a decimal, I can get this off of my calculator. So let's go ahead and look at our calculator really quickly, and we're going to compute both the p hat and the confidence interval. So in order to do that, I'm going to go to Stat and go over to Tests and go down to the one prop z int to create a confidence interval. I put in the x, which is 55, put in the n, which is 200, and we wanted to create a 95% confidence interval, so C level 0.95. I hit calculate, and I can see the p hat, my calculator computes it the same as I did, so 0.275. Here it says to write it as a percentage, so I'm going to move the decimal over to make it a percentage, so 27.5%. And then I have my confidence interval. I'm going to do the same thing. I want to convert it to a percentage, so I move the decimal over 2 places, so 21.312%. But it says to round to the nearest tenth, so I'm just going to round to 21.3. And my second one, if I move the decimal over twice, will be 33.688. And here, if I round to the nearest tenth, I have to round that up because the next digit is an 8, so that'll be 33.7%. Okay. So I have a confidence interval now, and 20% is not in that interval, right? It's not between 21 and 33. So the confidence interval does not contain it. And if I were to draw this out, my confidence interval goes from 21.3% to 33.7%. 20% is over here, right? It's smaller than 21%. So the confidence interval is entirely to the right of my 20%. Okay, so the confidence interval we found is entirely to the right of the 20%. Let's check and see if there are any other true statements here. So the confidence interval contains 20%, that's false. The sample proportion is different from the 20% shown in the pamphlet. That's true. The sample proportion is p hat. That was 27.5%. That's different than the 20%. So we're also going to check that one because it's a true statement and it says select everything that's true. Okay. But to answer the next part, should the pamphlet be updated, that's where we're really only looking at, does the confidence interval not contain 20%? Okay. So yes, the pamphlet should be updated because the confidence interval does not contain 20%. So that's what I'm going to look for. So yes, because we found, let's see. So in this one here, we say yes because we are 95% confident, right, because of our interval, that the population proportion is not 20%, right? It's between 21.3 and 33.7%. Okay. Any questions over that one? All right, so let's flip back to question 7 here. So this one has to do with z-scores, and we have to be really careful about wording here. Okay. All right. Morgan runs 2 similar races. For one race, okay, so let's just write this information down as we go. So I'm going to look at race 1. The times are normally distributed with a mean of 53.5 seconds. So that's the mean for the whole population. And a standard deviation of 4.4. Okay. Morgan's time, I'll write that as an x value. Okay, Morgan's time is 50.3 seconds. Okay, find the z-score for this time. So the z-score is always x minus the mean over the standard deviation. So we're going to take 50.3 minus 53.5 divided by 4.4. Okay, so I got my calculator, and we'll take 50.3 minus 53.5 and divide by 4.4. So we get a z-score of negative 0.727. Okay, it said at the beginning round your answers to 3 decimal places. Okay. So finding the z-score, negative 0.727. For the other race, so now let's look at race 2. The mean is 52.2. The standard deviation is 3.5. And Morgan's time on this one is 50.8 seconds. So when I compute the z-score, I'm going to take 50.8 minus 52.2 and divide by 3.5. And I get negative 0.4. Okay, so which time is better relative to all runners in the race? So a better time is a lower time, right? When you're running a race, the person who wins takes the least amount of time to finish the race. So what we want is a time that is as small as possible. Negative numbers are smaller than positive, right? So a negative z-score means you're below average. So our first race is more in the negatives than the second race. So Morgan did better relative to the other runners in the first race than she did in the second. Okay, so she is further away from the average based on number of standard deviations. So better that relative to the other runners, she did better in the first race. Okay. If I look at her actual times, in this case, her time in the first race is 50.3 seconds. That is faster than 50.8 seconds. So in this case, the z-score, the better z-score, is also the one with the better time. Okay, but that may not always happen. Sometimes you might have a better z-score, but it might be a slower time, okay, just based on the other runners in the race, right? The other, the rest of the population. Okay, does that make sense? Okay, any other questions off the practice exam that you would like to go over?